So, now we are going to discuss the details in this lecture today. That's the next topic. But you take a constant volume reactor, so it has this mixture of whatever fuel and air, okay. And then you specify what is the initial temperature, okay. And then you do calculations, okay. So, basically it is a kinetically driven phenomena, okay. So, this is the initial reactor temperature. Okay. I will show more details in the lecture today, okay, how the temperature in the reactor will change. Okay. So, this is the initial temperature, this is not the ignition temperature. So, the idea is as you reduce the, okay, you can look at this going from right to left. Okay. So, you go from this side, okay, then the temperature is increasing. Okay. So, this temperature is about like 1200 degree in initial, okay. This is about 600. Okay. So, you go from 600 to 1200, the ignition delay time decreases a lot, it is a log plot. It is about whatever 50 millisecond here at 600, and then here it is less than 0.1 millisecond. Okay, at 1200. Okay. So, this is the initial temperature of the reactor, okay, versus then you calculate the ignition delay time. So, I will show more details in the next part of the lecture. So, this material I am following the terms book. So, there is one particular chapter devoted to this material in the book. Okay. So, there they consider these 4 different reactors, and basically these are to demonstrate the effect of chemical kinetics on some combustion phenomena. So, the first 2 reactors here, constant volume or constant pressure, and then this is constant. They are basically same thing. Here we keep the pressure as constant. Okay. So, this is just shown schematically that as the combustion starts, reaction start, okay, to keep the pressure fixed, the volume will increase. Okay. So, the volume will be adjusted. Here you keep the volume fixed, so the pressure will increase. Okay. So, now to analyze this, so these are very simple reacting systems. Okay. So, actually now we are going, we studied the equilibrium, chemical kinetics, and now we are going to actual reacting systems. Okay. So, here in the first one, okay, or actually all of them basically, there is no dependence on space. So, there is spatially it is all uniform, spatially homogeneous. Okay. So, then things in these 2, okay, so all the properties are only function of time. Okay. So, compared to the equilibrium calculation, we bring now the time dependence. Okay. So, it is finite rate chemistry now, which is important. Okay. So, temperature will change with time, concentration of species will change with time, okay. And of course, here the volume will change, volume will increase. Okay. In constant volume is pretty similar thing, except the pressure now will increase with time. The third one is the well-stirred reactor, and this has been used a lot for experiments and also modeling. Okay. So, now this is the properties here do not change with time. Okay. So, what you do is you specify a residence time here. Okay. So, residence time is how long the mixture, so the mixture is continuously flowing. Okay. So, when it is flowing, you can see what is the residence time for the mixture, how long it will take for the mixture to flow out of the system, because it is flowing at certain speed. Okay. So, you control the residence time here in this, otherwise perfectly start. So, temperature, okay, the concentration, constant means they are not function of time. Okay. So when you start here, temperature may be 300 degree. Okay. So if you give very large residence time, what will be the temperature here? Okay. Large means infinite amount of time you give. Okay. So then it will be the adiabatic flame temperature. Okay. If you give less time, then it will be the mixture won't be fully reacted. Okay. Then the temperature will be less, and there will be more intermediate hydrocarbons. Okay. So by controlling the residence time, you can study the effect of chemistry. Okay. So basically, how do you control the residence time? You control the mass flow rate. Okay. So if you want to increase the residence time, you slow down, you decrease the mass flow rate. Basically, you decrease the velocity. Okay. So these three we'll discuss in more detail. This one I will skip, but I showed you an example today, plug flow reactor. This is the example we showed today. Okay. It's like a long tube, and you have the mixture flowing at some velocity, and then everything is a function of x now. Okay. Temperature will increase slowly depending upon what is the temperature here. Mole fractions will change with x. Okay. So this is the diagram I was showing near the end, the last session. Okay. So that's the steady flow reactor. Okay. In all four of them, there is complete mixing. Okay. So it's all controlled by, so there's no diffusion, no heat conduction. Okay. It's all controlled by just chemical reactions. Okay. So we can focus on the chemical reaction. Okay. So now we are starting with some basic governing equations. Okay. Since there is no variation with space, okay, the equations are very simple. Okay. So in the afternoon session, we'll discuss more general equations. So here they are only specific to this these three systems. Okay. So we have the continuity, the conservation of mass, species. So those students who are doing PhD, I think this is like a review. Okay. So there is no momentum equation required because everything is uniform in space. Okay. So you don't need the momentum equation. And then you have these constitutive equations or relations. So that applies to all the systems, equation of state, and then we say H is, so this looks familiar. Okay. So the way it is written here, so all of you remember now what is H? This. Okay. That's the enthalpy per unit mass. If it is per unit volume, just we put, per mole, sorry, H bar, that's the only difference. So H is per unit mass for the mixture. So this will be YI HI. So HI is the enthalpy of species I. Okay, again per unit mass. And then how do you write HI? It has, right? It's sum of two terms, right? HFI, enthalpy of formation, plus the sensible enthalpy. So this is from T reference to whatever is the temperature. Okay. So CPI is the specific heat for species I. Okay. So now more details of the equations. Okay. So the conservation of mass actually is very simple in this case. Okay. Because there is no flow. So one way you can say is that d rho dt is 0. Okay. But other way you just say the mass is constant now. Whatever is the initial mixture mass, the chemical reactions are going on. but the total mass doesn't change. Okay. So, the conservation of mass is very simple, that m is constant, okay, for both, whether constant pressure reactor or constant volume reactor. Okay. For the, this is called the well-starred reactor. So, what is the equation then? The mass flow rate now at the exit will be same as the mass flow rate, though the chemical reaction for the mixture doesn't matter. Okay. And this we are not going to study, but that will be the corresponding equation of conservation equation of mass, or equation of mass conservation, I should say. Okay, so that's the conservation of mass. Now, we will look at the individual species. Okay. So, here we will discuss few more details. So, here we are considering first of all the concentration. Normally, conservation of species mass, you will see later on when you do flames, we do not consider the concentrations, consider mass fractions. That is the more common approach. But for this particular, these reactors, it's probably more convenient to do in terms of concentration. Okay. And the Chemkin follows this also, this formulation also, that they use concentrations. Okay. So, anyway, there is no really big difference whether you use concentration or mass fraction. Because once you have concentration, you can get mole fractions. For mole fraction, then you can get mass fractions. Okay. All right. So, let us look at, so Xi this is the concentration of species I, let us say for the fuel. Okay. So, if we write dxi dt, because this is going to change now, right, for fuel as the reactions take place, xi will decrease with time for fuel. Okay. So, now xi by definition is Ni divided by volume. Okay. So, if you take the time derivative, now it depends whether we consider constant volume or constant pressure. For constant pressure, the volume is going to change. Okay. So, for constant pressure, it will be dNi dt. So, this will be for constant volume case. Okay. But constant pressure, now it will be plus Ni minus 1 over V square additional term, right. Now, dNi dt is what we discussed yesterday, that is the reaction rate for species I. Okay, so, this will come from the reaction mechanism times 1 over V. Wait a minute, no, V gets consumed, because this is per unit volume. Okay. So, this is, what are the units here for this? Okay. Mole or kilomole, meter cube per unit time. Okay. So, this is already by definition just the reaction rate in terms of moles. Here now we have minus N over V, Ni over V is again Xi. So, this is just Xi and then times dV dt. So, this is the first equation there. So, reaction rate term, the rate of consumption or production of the species I per unit volume, okay, and that is the rate of change of volume term. Okay. For constant volume case, this term will drop out. Okay. So, this will be the term then, right. Now, well-started reactor we are going to discuss a little bit later, but there is physically it's very easy to understand. This is the mass flow rate of species I at the exit, and this is the mass flow rate at the inlet. So, the difference will be due to chemical reaction. So, you can ignore this symbol, you can go directly here. So, the difference in this mass flow rate is the rate of fuel consumption, right. If it is CO2, then it will be rate of CO2 production. So, for different species this value will be different, right, omega I. So, this is again per mole, rate of reaction per mole for the species I. So, you multiply by the molecular weight, or we can do first take per unit volume and then multiply by the volume, and then multiply by the molecular weight. So, this gives you the rate of consumption in terms of kilogram per second. So, this is just the total rate of reaction per second, kilogram per second. So, the difference in the mass flow rate is just the rate of reaction. So, these systems are easy to also understand the material we have discussed and the conservation principles. So, this is the conservation of species mass. Then only thing left is the temperature or the energy equation, and this is very interesting. So, now I can relate this to what we discussed last 2 days. So, this is basically the first law of thermodynamics, right. Remember the equation we discussed first day, the dH is equal to delta Q for constant pressure system or constant pressure process. So, same equation we are using, but now everything is a function of time. So, instead of dH we write the total enthalpy, rate of change of total enthalpy equal to rate of heat transfer. So, later on either today or tomorrow we will see a very complicated 3-dimensional energy equation, but it is based on this principle. Only thing is you'll have some work done and some other terms will appear there, but basically it's this equation. So, rate of change of enthalpy for constant pressure process is equal to the rate of heat supplied. Now, H is mass of the mixture times H, right. Now, M does not change with time, so you can bring it outside. So, that is equal to Q dot. So, that is the basic form of the energy equation. So, using that equation we can get the equation for temperature. So, this is the main reason I like this kind of simple system. That idea is you use the energy equation which is in terms of enthalpy, but actually the equation is for temperature, because for equilibrium we did the same thing. We started with this kind of equation and then we ended up with the equation for adiabatic flame temperature. So, same thing we are doing here, it's just it is in a different way. So, let us go through a couple of steps for the derivation of this equation from this equation. Let me use the other color, I think it writes better. So, m dH dt sorry, this is small h. So, the total H, you can also write which is mH or it is equal to Ni Hi bar. Okay. Ni is the number of moles. Okay. So, if I use this, okay. So, now I can differentiate this, by individual terms. So, this will be sum of Ni dhi dt Hi dni dt. Okay. Now, what is Hi? Hf, oh, this is all bars. Actually, we don't need bar on the end, only on H. So, Hi bar is Hfi bar Cpi dt. Okay. So, what is dhi dt? This is a constant term, right? It does not change with time or temperature. So, this will give us Cpi dt dt. Okay. So, this term here, I will continue here, is just Ni, and what is Ni? Xi times V. Okay. Times Cpi bar, this is, yeah, there is a bar here. Okay. And then the next term, of course, we write dni dt is omega I times actually omega I, right? Oh, no, there should be a volume, because this is total moles. Okay. So, times volume. So, then this term, okay, m ds dt has these two terms. Okay. Okay.
CPA value, you have to take an average.
No, this will change with time. It's not average. Okay. Because when you have this, when you do dhi dt, so the derivative of this, because this is t reference, this is t here. So, when you take the derivative, you just get Cpi. So, this is exact, no approximation here. Okay. So, that term gives you these two terms, and now we can write this in terms of, because this is equal to q dot. So, you can take this term to the other side, and there is a volume here. So, you divide q dot by V, and then write this term, okay, and then xi Cpi. Okay. So, this is very interesting, because what is xi times Cpi sum? There should be a bar here which is missing. What is xi Cpi bar sum? Right? That is the Cp of the mixture. So, basically it is Cp times dt dt. Okay. So, whatever heats you are supplying, so there are two sources here. This is the heat supplied from outside. So, for adiabatic system, again this will be 0. Okay. So, for adiabatic system, you have only this term. So, if you write that way, So what you have is xi Cpi dt dt okay. So this gives you simple energy equation that in adiabatic system the rate of heat change due to chemical reaction changes the temperature. Okay. So that's the rate of increase of energy due to the chemical reaction. Okay. So this is actually very similar to the equilibrium equation we had for adiabatic flame temperature. Only thing is here no temperature changes with time. Any questions? So we are using the first law of thermodynamics, okay, for a little more complex system compared to what we studied, last 2 days. First day we studied a mixture at equilibrium condition. Now things are changing with time. Okay. So this is for constant pressure system. Okay. For constant volume, so this again comes from our first day lectures. Because for constant volume we start with delta U equal to delta Q, right? Change in the internal energy. Okay. So now we write this as m du dt equal to Q dot. Okay. And if you go through the same kind of steps, that this term is dd dt of sum of ni ui, take per mole, and then take the derivative. So again you end up with dni dt ui bar plus dui dt, and dni dt will give you omega I times volume. Okay. So whereas this one, no, I messed up this. Let me change this. This is here. This is omega I dot times volume. Okay. The next term is ni dui dt. What is dui dt? Cvi dt dt. Okay. So this term is written, in the second equation. So this term here you write as Q dot V, okay, and then ui omega is this term. Okay. So it's very similar, except now you are using U instead of H, okay, for constant volume system. So here you have H, here you have U, here you have CPI, now you have CPI. Okay. Otherwise the same term. Okay, so now we have, so let's consider constant volume. Okay. Oh no, wait a minute, let's consider constant pressure first. So for constant pressure, what are the equations we need to solve? Okay. So mass is constant. So you have the equation for concentration as a function of time. Okay. So what you need for this? Okay. You need the reaction rates. Okay. So that means you have to supply the reaction mechanism. So if you are doing for hydrogen, so last 2 days we have discussed what is the mechanism, one of the mechanisms for hydrogen. So you have to have that. From the mechanism, you can calculate the reaction rates. Okay. So each reaction rate, like say for example, you take hydrogen fuel. So what is this term for hydrogen? Okay. So there were a list of like 21 reactions. So you have to see, okay, which one is consuming or producing hydrogen. Okay. So omega I for hydrogen will involve those reactions. And for each reaction, what is needed? Okay, it has a temperature there, right? How do you remember the reaction rate term? It's K. K is A, the pre-exponential factor. Okay. I can actually go back there. Yeah. Let me just quickly. Yeah, exactly. Okay. So here you have this is omega I dot. Okay. So which is coming from, so what is omega J? That's for particular reaction. J is the reaction number. Okay. So you can, from the mechanism, you can see which reactions have hydrogen. So then you can write this. So the main point is that in that equation which we are discussing, okay, the omega I term comes from the mechanism. Okay. So if you are using a software, you have to supply the mechanism, that's all. Once you have the mechanism, the software will calculate those reaction rates. Let me see if I can go from here to the other lecture. Okay. So for this term, you need to supply the mechanism. Okay, if you have heptane, it's the same thing. The mechanism will be bigger. Okay. So anyway, you have basically now. So how many equations you have for Xi? If you have hydrogen, there are like 8 species, so you'll have 8 equations for the 8 different species. If you have heptane, you may have like 100 species, so you'll have 100 equations. Okay. But they are all very similar. Okay, they are all ordinary differential equations. Okay. And then you have another one more equation for the temperature. So this will be the equation for the temperature. Okay. So for hydrogen, you have like, so let's say 8 equations for the species, 1 for temperature. So 9 equations you have to solve simultaneously. So when you do use numerical method for solving, you have to be aware of, because different reactions, they occur at different rates. Some reactions are very fast, some are very slow. Okay. So you have to accurately predict the reaction rates of very fast reactions also. Okay. So your time step will be determined by the fastest reaction rate, because you have to resolve that, that occurs in very small time. Your time step has to be smaller than the rate for the smallest reaction. But anyway, there are softwares available. Chemkin is just one of them to solve, like Cantera will also do the same thing. Okay. Solve this system of differential equation, ordinary differential equation. And all of us know that we need to provide the initial condition. Okay. So we provide what is the initial volume of the reactor, what is the initial composition of the mixture, initial temperature. So you provide the initial values of Xi. Okay. For example, what is the initial value of CO2? 0 will be 0. Okay, so you only have to provide equivalence ratios, which will give us what is the concentration of fuel species O2, N2, basically that's it. Unless you are doing something else, maybe you want to study the effect of CO2 on the combustion, then you provide some CO2 or some other species. So, provide the initial conditions, then you have a set of ordinary differential equations to solve, and then you will give you solution as a function of time. Okay. So, the fuel concentration will start decreasing with time. Okay. Some other species, like let us say if it is hydrogen, then hydrogen will decrease, oxygen will decrease, OH will start increasing, H2O will start increasing. So, you will see all these. So, I will just show you the results. In addition, you can also get volume as a function of time. So, you can write equation for that. Let me go PowerPoint more. So, you can use equation like this for the volume, because now you are calculating xi as a function of time. So, at every time step you can also calculate volume, because mass is fixed. Okay. So, this simple equation, because mass times the total number of, okay, or the mass of individual species, that gives you the volume. Okay. So, this times volume is the total mass. So, pressure is constant. If you have a constant volume system, then since you are calculating xi, you can calculate pressure as a function of time. Okay. So, this will be for constant pressure system, this will be for constant volume system. Okay. So, then I will have some results. So, I am using this hydrogen air mixture. So, this is for using the same mechanism I was been showing as an example, Conair mechanism, which is like 20, I think about 21 reactions, 8 species. Okay. So, you start with some initial condition at time t equal to 0. So, this is the hydrogen. So, from concentration I change it to mole fraction. Okay. So, this is the hydrogen, and where is the oxygen? This is the oxygen. Okay. And this red is the temperature. Okay. So, for this case the initial temperature was 1000 in the reactor, pressure is 20 atmosphere, okay, equivalence ratio was 1. So, you control these conditions. Okay. And then as I said, then you supply the mechanism. So, volume is constant. Actually, this give like as a project to students in the class. So, this is from the report from one of the students. So, now you can see that this time is in millisecond. So, up to 3.5 or 4 millisecond, almost nothing is happening, very slow. So, because all those initiation reactions are starting, okay, at this 1000 degree Kelvin. Okay. So, once the radical pool builds up, then see how fast the temperature increases. Okay. For hydrogen we say that's an explosion, hardly takes any time once the reaction starts. Okay. So, it is almost instantaneous increase in temperature. Okay. And then you can see almost instantaneous consumption of fuel. Whatever is the fuel mass fraction here, 0.3, it drops to almost 0, okay, in some microsecond. Okay. So, this phenomena is occurring at microsecond. And then there are some other species here. I think this is H2O2. And you see H2O, this is a very interesting, it starts forming only here. Okay. And then of course, it increases almost instantaneously. Now, you can focus on this region here and zoom it. So this is how the things are changing in time. So this is from 4.05 to let's say 4.06. Okay. So this is like a couple of microseconds. Okay. So now you can see the details what's happening in this region. So look at the hydrogen mole fraction, how it's decreasing. Okay. And this is oxygen, the purple. Okay. And temperature is red, so it's around 1000 or 1100. So this is how the ignition is taking place. Okay. So these calculations was basically to see the ignition phenomena. Okay. So this is temperature. What else? Then you have these other species. So you can look at all the intermediate species, OH. There are only few here. Okay. So all the intermediate species. So most of them are produced and get consumed in this region. Okay. Finally, you get only H2O. H2O is this value here, the blue. Okay. The other species mole fractions are very small. Okay. So you start with H2O2 and you end up with H2O basically. Okay. Now, if you do the equilibrium calculation, it will give you only these values. Okay. It will not give you what's happening with respect to time. Okay. So that's the limitation of the equilibrium calculation. Okay. Equilibrium approach. It gives you the final properties. Okay. So whereas with this kind of model, you can study what's happening with time, and this is all chemical kinetic effect. Okay. If you decrease, you can decrease or change the equivalence ratio. So you can do a lot of different things. Change the initial temperature, pressure. Okay. By changing the pressure, you can see that those explosion limits we talked about yesterday. Okay. As you keep increasing pressure, maybe the ignition delay will decrease in certain region. Okay. So you can study a lot of. So this is a very good learning tool also, analysis tool as well as learning tool.
Sir, this time step in microsecond or this?
Oh, this is not time step. This is the ignition delay time. Oh, this is a very interesting question. Yeah. So how do you define, that the ignition has occurred? Okay. So people use, two criteria. One is they say, okay, the temperature in the system increases by over one time step. Time step was very small. I don't remember if there is a time step here. It was less than microsecond. Okay. So over one time step, if the temperature increases by 400 degree Kelvin, so you say that is the instant ignition has occurred. Okay. Or you define by OH value. Okay. So you can say by certain percentage. What we do normally, we say, okay, if the OH value reaches 50% of its peak value, okay, then we say that's the ignition delay time. So there are different criteria, but typically ignition delay does not depend too much on the criteria you use. As long as your criteria is consistent, useful. You cannot say temperature increases by 10 degree, okay, or 2000 degree. As long as your criteria is reasonable, you get almost same ignition delay time. Any questions?
Sir, the first diagram is it for constant?
Both are same, constant volume. Yeah, it just it's very difficult to see what's going on. It looks almost like everything is like explosion. How fast it increases, like a step function. So here you can see the details by zooming.
Your pressure plate also can be done pressure plate.
Oh yeah, it actually is there. Yeah, good question. This is how the pressure looks like. So all this is only plotted in this region. Okay, starting with 4.05. So the initial pressure was 20. At this time, it's already reached almost 30. You don't see in this plot. Okay, so it's almost like 28 or 29. And then where the ignition occurs, it increases very rapidly. And this is the final pressure. Again, if you do the equilibrium calculation just by hand, you can predict the final pressure. Okay. Because now you have to calculate adiabatic flame temperature at constant volume. Okay. And then, using the equation of state, you can predict what is the pressure after your combustion. Okay. So it will give you this final value. All the final properties can be predicted by using the equilibrium model.
This is a constant volume reactor calculation, sir. Ignition delay to find out the ignition delay. Is it possible to calculate ignition delay in a constant pressure reactor?
Yeah, you do same thing, except now you say impose that condition that is constant. So your equations will slightly change. Okay. For constant volume, constant pressure, you use these equations.
In both cases, we get the same value. For
Ignition, no, it will be different. Yeah, let's discuss that. That's a very good question. Okay. So think which case ignition delay will be less or more, constant pressure or constant volume.
Active pressure will be more.
Constant pressure.
How many for constant volume?
Constant volume will be less. Ignition delay will be less.
Exactly. Constant volume, it will be less. Okay. Now think why it should be less.
Temperature is
Because adiabatic flame temperature is. So at every step, temperature will be little bit higher
reaction rate.
for constant volume case. Okay. Because some of the energy is going in to increase the volume in the constant pressure case. Okay. So ignition delay will be less for constant volume system. Okay. I think there is a graph for the constant pressure. So you see for constant pressure, the ignition delay time is 4.38 millisecond. Okay. Whereas for constant pressure or constant volume, it is 4.05. Okay.
So zero is start of mixing of the fuel and
It's totally mixed when you start. Fuel, you just specify equivalence ratio. So it's a well mixed system.
zero is sort of what does zero indicate?
No, because you are solving a ordinary differential equation. So your solution starts from initial condition. So that is a 0 point. So that's the 0. Okay. Yeah, all these plots will change if you change the equivalence ratio or temperature or pressure. But we are always starting with 0. That's the initial condition. Now, this constant volume reactor or constant pressure reactor.
Sir, one more.
Yeah,
So
sure.
at the time t equal to 0, the temperature what shows is that ignition temperature. Is it, sir?
No, this is just the initial
Or
temperature.
constant volume is constant.
Uh,
At time t.
no, I don't know whether you can get really the ignition temperature. So here we have 1000, right? That's the initial temperature. So if you do at 900, okay, it will ignite, but the time will increase now.
ignition time will increase.
Ignition time will increase. So, if you look at this sudden rise This happens at 4.05 millisecond here, right? So, if you decrease this initial temperature to 900, this is going to go maybe 5 millisecond or 6 millisecond. If you keep decreasing the initial temperature, it's going to become like 100 millisecond. So, it's still going to ignite, but for practical purpose we can say okay, no ignition because it takes forever to ignite. But in principle it's going to ignite at some time. Okay. If the temperature is like 400 degree initial, okay, it probably takes few seconds, not milliseconds to ignite. Okay. But this mixture will still ignite. It will take forever, for a long time. So
If it is 400 degrees centigrade, then it will never ignite, isn't it? Because
I
it's
think
a
it will
hydrogen-
probably ignite, maybe it will take like, several seconds or more than several seconds. Okay. Eventually it will ignite. Because that's what equilibrium tells us, right? Okay. Now here I thinking like we can also plot the entropy of the mixture, and that will will also keep changing, keep increasing until equilibrium. Anyway, so this is constant volume, constant pressure, two systems, and these are very commonly used to calculate ignition delay times. Of course, you can also study the ignition phenomena, how all the species are changing with time, how the temperature and everything is changing with time. So, you can study the details, but a lot of people use this to just predict ignition delay, especially they take a new mechanism and there is a lot of data on ignition delay time. People use shock tube, the rapid compression machine, and they reported the ignition delay. So, they validate their mechanism by comparing with the experimental data. Okay. So, they use this constant pressure or constant volume systems. So, this is one example from one of our recent papers. So, Shao Fu was the PhD student who just finished last year. So, this is from this paper are also from his thesis. So, what we are doing, these were like diesel combustion computations using a software. So, we were looking at injecting like a diesel fuel, okay, in a methane air mixture. Okay. So, it's like a dual fuel. So, the methane or the natural gas is coming with air and then you inject the liquid fuel. Okay. But this is just using constant, I don't remember whether this is constant pressure or constant volume. This is probably constant volume calculation. So, for
Constant pressure,
Constant
sir,
pressure,
basically.
two pressures are being used.
okay, the constant pressure. Okay. This got changed. This is phi equal to 1. Equivalence ratio is 1. Okay. So, this is just showing the ignition delay now. So, we were changing the initial temperature. Okay. So, this now you can understand fully because we just discussed. So, this graph here the initial temperature was 1000 degree. Okay. And then this is the ignition delay right here, which is 4.3. So, now we are changing the ignition the initial temperature and then just looking at what is the ignition delay. Okay. So, this is the ignition delay for heptane, and again it shows that behavior it's called NTC behavior. Okay. So, it does not vary monotonically with temperature. Okay. And then it's comparing with the experimental data, and you see still there are a significant difference between the experimental data and prediction. But this is considered acceptable difference because there's so much uncertainty still in the mechanism. So here we are using one simple reduced mechanism called Chalmers. So Chalmers, okay, has probably 200 or so reactions. That is considered, simplified as the reduced mechanism. Because crack, so this comes from, there's a kinetics group in Italy, in Milan Polytechnic, Ranzi, that's the Professor Ranzi. So you can download this the mechanism from their website. Okay. But only problem is these mechanisms are quite big. I don't remember, this crack is like something like 4,000 or 5,000 reactions. So it takes long time to do this calculation. So even for simple system like homogeneous reactors.
Sir, do we not observe NTC in methane combustion?
Yeah, you do not observe that. And also you see that the ignition delay is much longer for methane. It's very hard to ignite. So basically, the purpose, of course, this exercise was because we are going to use the Chalmers mechanism for the diesel calculations, which are like 3D calculations. So we wanted to show that, okay, it gives reasonable ignition delay time, okay, using that mechanism. But anyway, for us, so you can see, this is using constant pressure reactor, formulation we discussed today. Okay. So there are a lot of things you can do using these, simple systems. Okay. So the third system we are going to discuss is the well-starred reactor. Now, for gas turbine combustion, analysis, this is commonly used. Okay, because this well-starred reactor, it gives you some, initial values for blowout conditions, flame blowout. So here we are not studying any flame because it's all homogeneous mixture. Okay, so there's no, you cannot call anything flame here. This is a combustion of homogeneous mixture, but it gives you some initial estimates for blowout conditions. Okay. So people use this, for, in gas turbine industry. Okay. Typically, they don't use one reactor; they use like, reactors in series or reactor in parallel. Okay. So they have well-starred reactor, perfectly started. There are different reactors they use to model, the gas turbine combustion. I'll give you one example, little bit, in a few minutes. So here, what you have is you have a fuel air mixture coming out here, going in here, and you constantly keep the system completely mixed. So in the real system, they have these mixers, some rotation, the flow. So keep it all well mixed continuously. Okay, so there is no variation in space. Only, so you have a fuel air mixture going in here, and then depending how much time the mixture has, so this will be the product. Okay, so here the temperature may be say 400 degree. Here it will be, if you give lot of residence time, it will be very close to the adiabatic flame temperature. Okay, if you give less time, of course, then temperature will be less. The equations are very simple. Here we just discussed those equations that this is the mass flow rate at the exit. So this is the mass flow rate at the inflow. So for example, H2O, if it is hydrogen air mixture, what will be H2O here? It will be 0. There is no water going in there. Okay, so this will be 0. And this is just the rate of mass flow rate out due to chemical reaction. Okay. So either you can use this equation, or then you can change it to mass fractions. because what is mi dot? Mi dot is m dot times yi. Okay. So, you use the mass fraction, same equation. So, if you specify the mass flow rate, okay, then this is you are specifying, right? Okay. So, you can calculate this value. All you need is the calculation of reaction rate. Okay. So, in general, it looks like a very relatively simple calculation. You just need to calculate the reaction rates. Okay. So, you can predict the mass fraction of all the species at the exit given this value, and then you calculate the reaction rates. Okay. And then this equation you see is exactly same, almost same what we studied in the on first day. Okay. That's the first law of thermodynamics, right? So, Q dot of course we consider as 0 adiabatic system, but if there is a heat loss, if you want to study the effect of heat loss, you can include that. Okay. Otherwise, we are just writing this out now. H out is yi out times hi sum. Okay. And then in the same way, so we use this equation. It will give us hi out, because yi out is calculated from here. So, this gives enthalpy at the exit for each species, and from there you can calculate the temperature. Okay. So, this equation is again for temperature. Okay. Temperature where? At the exit. Okay. So, these equations you use to predict the values here, that is all. Okay. You specify the mass flow rate, and so you specify the mass flow rate. What is this? So, that is the volume of this reactor, okay. And then you use the density. So, this gives the mass inside the reactor. So, you divide by the mass flow rate, this gives you a flow time or residence time. Okay. So, you control this residence time by controlling the mass flow rate. Okay. So, now in the interns book, okay, this is like for like a student exercise. So, we will not go through that example, but what they do is in the book they consider just 3 species, okay, fuel, oxidizer, going to products. Okay. So, it's extremely, so then they have only basically 3 equations like this for the 3 species, and then you have the idea they can simplify these equations, okay, to understand a little more physics, okay, what's going on. And then also for students, it's easy to program, if you just have 3 equations. Okay. So, there is an exercise there. I will just show you the result of that. Okay. So, what is shown here is, okay, you are increasing the mass flow rate along the x-axis. Okay. So, as you increase the mass flow rate, basically you are decreasing the residence time. Okay. So, you are controlling how much time the mixture can react. Okay. So, as you decrease the time for the mixture to react, okay, so I didn't see the temperature here. Oh, this is the temperature, yeah, sorry, I was looking. Okay, so here now, okay, if you look at the fuel, so when the mass flow rate is very small, we are giving lot of residence time, right? So then all the fuel is consumed. There is very little fuel. Okay. Now, as you increase the mass flow rate or decrease the residence time, so this becomes like the unburnt fuel. Okay. Now, this is only because you only have 3 species. If you consider a detailed mechanism, then there won't be any fuel. You will have intermediate hydrocarbons. Fuel gets consumed. Okay. And same thing, there is a lot of oxygen left because these are the only two reacting species. Okay. And the product mass fraction will start decreasing if you decrease the residence time. Okay. And same thing happens to temperature. Here it's almost adiabatic flame temperature. Okay. What is zero residence, zero mass flow rate? Okay. That means very, very small mass flow rate. So, the residence time is very large. Then the mixture becomes all at equilibrium. Okay. Then the temperature is like the equilibrium flame temperature or the adiabatic flame temperature.
So that will be compared to constant volume reactor.
Not constant volume, we just do equilibrium calculation. So that will give you these values at the axis.
So the mass flow rate is almost zero.
Yeah.
So the system is also doesn't you don't change the volume of the system. So in such case, will the result be comparable to that of the other kind of reactor?
Oh, see, in that one you are like you are calculating everything as a function of time. So there is no time, there is only residence time here. Okay. Now we have more realistic calculation on the next couple of slides.
Sir, what is the effect of volume of the well split reactor? The effect of what should be the value we can take? The effect of volume of the well split reactor.
Yeah, actually that's a very good question. If you change the volume, then the mass flow rate effect will be slightly different. Okay. What actually people also do, they keep the mass flow rate fixed. Okay. They keep changing the volume. Okay. The idea is to change the residence time. Okay. So for those who are not very familiar with the residence time, it's like when you put a toast in a toaster, and you have seen those toasters where the bread keeps moving and then it comes out. So there you are controlling the residence time, whether you want it dark. Okay. If you want very dark, then you increase the residence time. Right? Then it comes, it goes, it moves, very slowly. Okay. If it moves very fast, okay, then the bread will come almost like initial bread, right? So it's the same thing. You're controlling, it's like a tube. You're controlling how much time the mixture spends in the tube. That's the residence time. The residence time is used, in the real combustion analysis. So these are the detailed results. So here we did for syngas. So it's a 50%. Syngas, this composition can change a lot. So this is just for one particular case. We have 50% hydrogen and 50% CO. So temperature is on this side. These are all the mole fractions. So now we are plotting with respect to residence time. Okay. So when the residence time is very large, okay, you get the equilibrium properties. So you see the temperature now is temperature is about 2400. Okay. And this is the H2O mole fraction. Okay. There is a little bit of CO left here. I think the equivalence ratio was, if I to guess, it's 1. There's some CO left. Okay. But others, H2O is almost 0, OH is almost 0, everything else is almost 0. Mainly it is H2O. Okay. Now you'd start decreasing the residence time. Okay. You start continually decreasing. Temperature will decrease. H2O value will decrease. Now you see, what are the fuels for this case? H2 and CO. So CO starts increasing and H2 starts increasing. Okay. So there is a minimum residence time where there won't be any combustion. Okay. So the minimum residence time you call as the blowout condition. Okay. So to analyze blowout conditions, you calculate the minimum residence time. Okay. That corresponds to the blowout condition. Okay. So if you want to just analyze the blowout properties, then you calculate the minimum residence time as a function of equivalence ratio, okay, as a function of initial temperature, pressure, whatever you want to do this. Okay. So I have some results on the next slide on the blowout behavior. So here the minimum residence time for this case is right here, which is 0.05 millisecond. Okay. So now for this syngas mixture, okay, so each point here represents all of these calculations, that you keep changing the residence time, keep decreasing it until you get blowout. So all those minimum residence time points are plotted here now as a function of equivalence ratio. Okay. So this is a very interesting plot. Okay, we can forget about for the timing the composition, just take 50% case, 50% CO 50. So the minimum residence time, okay. So this is the optimum equivalence ratio. Okay. So if you want more desirable blowout, what should be the residence time? It should be as small as possible, right? Because that means you have a lot of mass flow rate, you can sustain a flame. Okay.
Sir,
Yeah.
reducing the time, residence time means we are deteriorating the mixing phenomenon.
Yeah, see here mixing is all instantaneous, it's all well mixed. Yeah, but you are right, like in real cases, residence time will be the mixing time also. Yeah, okay. But here, we are taking idealized system so that we can focus on certain aspects. Okay. So it's a well mixed system. Okay. So residence time is just the flow time. Here. Okay. But other way to look at it, if you keep increasing the mass flow rate, right, the flame eventually will blow out. So the maximum mass flow rate you can sustain, that is the minimum residence time. Okay. So that's what we are plotting here. So you can think of the maximum mass flow rate or minimum or the residence time. So it is minimum at about 1.5. Okay. So the flame will sustain over the wider conditions at equivalence ratio 1.5. As you increase the equivalence ratio, the minimum residence time increases. Okay. To understand this simply, what happens to temperature as you increase the equivalence ratio? It will decrease. So this plot is very similar to if you plot the adiabatic flame temperature on the x-axis. Okay. It will be exactly almost similar. So since the temperature is lower, the residence time is higher. That's the minimum time the combustion is sustained. Okay. So on the red curve, if you go below this, what it means? What does that mean? If you lower the equivalence ratio here from this value, you go below, okay, that means there is no flame. It's all blown out. Okay. Or did I say the other way around? No, the other way around. Okay. On the red point, if you go to the left, this is a blowout. Okay. If you give more time, then there is a flame or combustion. There is no flame here, but You can think of flame or combustion, same thing. So, if you go to the right, you have sustained combustion. Left is blowout. Okay. So, at this point, sustained combustion you can have at a lower time. Okay. And then this also depends on the composition. If you have more hydrogen, for example, 80% hydrogen, then everything shifts to the left. Okay. Then you can have combustion even at higher flow rates. Okay. Higher flow rates. Also, we have to realize these are like lots of calculations, because for each point you have to do several calculations to find the minimum, and it's not always easy to find what is the minimum, okay, because you are finding a condition where there is no combustion. Okay. So, when you are doing calculations, sometimes the program doesn't converge. Okay. Then you don't know whether it's no combustion or it's a numerical thing. Okay. So, you have to do a lot of trial and error to find the minimum residence time. So, combustion at extreme condition is always more challenging. Okay. This is the same graph plotted in a different way. Here we plotted with respect to residence time. Here it is plotted same thing with respect to flow rate. Okay. So, now you can see that this is for 50% hydrogen. You go 80% hydrogen, you can have more flow rate, mass flow rate for a sustained combustion. Okay, now, as I said, this is just one reactor. People use like series or multiple reactors to study blowout. They also study the NOx emissions, other things using these models in gas turbine. I think few years back this was much more common because the CFD was very challenging. Okay, it was very demanding. So, now people can do direct CFD of the real combustors rather than using this model combustors with a number of these reactors. But I will show you some results from the older study. Where they use reactor models for blowout and also for emissions. So, they have a real combustor, also model combustor. So, let me see. So, here you see they are using PSR1, PSR2, PSR3. So, they are using 3 perfectly starred reactors. Okay. The calculations become a little more complicated when you have more than one, because some are in parallel, some are in series. Okay. But people over the years have done a lot of these reactor models, used reactor models to study blowout or to study emissions. Because again the idea is using the simple model you can use very detailed chemistry, which you cannot do if you use a real combustion, gas turbine combustion. So, there are lots of papers, Pratt and Whitney, different gas, the engine companies have done a lot of this work. Nowadays, because of the CFD capabilities, this practice has gone down to some extent.